Welcome back. We're about to get into some sections where we talk about waves, and so in case you haven't thought about them in a while, I thought we'd have a warm-up where we talk about some properties of waves, things we can measure about waves, and then you'll be ready when we start doing number crunch about them. So the most obvious kind of wave that everyone has seen is ripples on the surface of water. That is a wave shape. Sound is a wave that happens when you bump a mass of air and ripples travel through that, pressure waves. You can take a rope or something like that and whip it back and forth and cause a wave shape to appear in it. That's a legitimate wave. And we're going to see in this unit, spoiler alert, that light and some kinds of radiation are actually waves made up of electricity and magnetism that can travel through space. And there are a few things that all those waves have in common that we can measure about them, but before we get into those, let's just talk about the shape of a wave and some landmarks that we can find on it. So, in theory, a wave can go on forever and have an infinite number of ripples, but when we break it down, we want to see what a small repeatable piece of this is. And typically we talk about, starting from here, a single wave will consist of one hill and one valley. So it'll go up once and down once. And once you've done that, you've completed one wave. So right about here, I would say, between those two blue dots is a single wave. It goes up, it goes down, and now it's ready to go again. Up and down, that's the end of another wave. Up and down, finishes another wave. Up, and it doesn't finish this last wave. So here we have one cycle, two cycles, three cycles, and roughly half of the... It didn't finish the fourth cycle, it got about halfway through. So each of those pieces, which consists of one up and one down, is one wave, or sometimes we call it one cycle. And you can count how many of those that there are in a single, in a waveform. You could say that's one. To here would be a second one. Up and then back down would be a third one. And then we have something like half of another unit. So we could say that this thing is 3.5 waves long, or 3.5 cycles. Now, if you have a wave that's bouncing up and down, it goes to a maximum here. So some of the landmarks that we can identify on a wave are a maximum. If you think of a water wave, this is the highest that the water ever gets. At the bottom of each of these, there is a minimum, the lowest that the water ever gets. And right through the middle, there's like the average depth of the water, which we often call the midline. Sometimes they call it the average. But midline is pretty common. That's what I'm used to using. And now I have to apologize because a lot of these things have multiple names, and I'll try to give you all of the common ones. The top of a wave, the highest that it ever gets, is called the maximum. It is also called a crest. Crest being the highest point on something. The minimum is also called a trough. If you think of like a water trough that you give animals food or water in, it's a bowl shaped like this, and so that shape makes sense for a trough. And in between, the points where you're right on the midline, so I feel bad making those all the same color. The dark blue ones are the beginnings and endings of cycles, and these other ones are just other points that I'm marking. Every point where you cross the midline going up or down is called a node. So, node, crest, node, trough, node, crest, node, trough, node, crest, node, trough. That's what every wave is going to do as it travels. And with those as landmarks, we can start taking measurements of a wave if we want to know how big it is or things like that. Waves actually have physical measurements, and they're hard to measure with a water wave because water waves are moving and going past you. They don't sit still while you whip out your ruler. But if you were blindingly fast, or if you could stop time, or if you could take a photograph and then take some measurements off the photograph, there are some distances that you can measure for a wave. One of them is, how far is it from the beginning of one waveform, or one cycle, to the beginning of the next? We call that distance a wavelength. It's a physical distance. They're usually measured in meters. So for a water wave, the wavelength could be 5 or 6 meters. If it's little tiny ripples, it could be centimeters. If you drop a rock in a pond or something and you're getting little tiny bumps, this could be a very short distance, but that's always the distance from the beginning of a waveform through one crest and one trough and back to the middle. That distance, they don't call L, because L is already used for too many other kinds of lengths, so they use the Greek letter lambda, which is their lowercase l. So that symbol lambda means wavelength. And sometimes we can measure this, sometimes we have to work it out by using a formula that we'll see in a few minutes, but that's the horizontal distance along a wave. Another thing we can measure about a wave is how high it is. And there's two places that you can measure this. You can measure, actually I won't put that there, I'll put it right in there. You can measure how high are the crests on a wave, or you can measure how deep the troughs are on a wave. Those distances are always the same. And either one of those distances is called the amplitude. So that distance is the amplitude from the midline to the crest, or from the midline to the trough is also the amplitude. If you're in math, you might be used to calling this the vertical stretch factor. That's still basically true, but in physics we use the word amplitude a great deal. So the amplitude is either the maximum value minus the midline, meaning the distance from the maximum to the midline, or it's the distance from the midline to the minimum, or the last one we use is it's the maximum minus the minimum divided by 2. So what that means is you could measure from the very top of a wave all the way to the bottom of the wave. That's 2 amplitudes. Cut that in half and you've got a single amplitude. Right? So we can measure wavelength for a wave. We can measure the amplitude for a wave. And there's one more important thing that we can measure about a wave, but I'm going to clear this out so we can talk about that. And let me put a wave back in our screen. So far, everything I've drawn has been distances, but there's also something about a wave that you can measure with a stopwatch. For some waves, especially things like sound where you can't see them to apply a ruler to them, one kind of measurement that you can take is you can stand in one spot, and as the wave comes at you, you measure how fast waves are going past you. So if you have this wave coming at you and you measure in 1 second how many waves go by, that'll tell you something. You could stand there, and I'm going to do this in slow motion so that I don't have to move things too fast, but if you count a second and it goes 1,000. Sorry, let me see if I can scoot that whole thing over. Okay, let me run that again. So here's you, the observer. As soon as the wave starts to hit, you start counting how many waves go by, and in a second you get 1,000. After a second, how many waves have you seen? Remember how we count? Starting from here, we got a crest and a trough. That was one wave that went past your head, and then a crest and a trough, and I made it easy for myself here. Exactly 2 waves went past you. You saw 2 waves in 1 second. That measurement is called the frequency. And it's measured in waves per second, or sometimes they use cycles per second. Remember we said one of these ups and downs is called a cycle. You can get cycles per second, you see that sometimes. And the metric unit for this, because it's faster than cycles per second, is they use hertz. Heinrich Hertz was a physicist who studied waves, and his name is now attached to the unit for frequency. It's hertz if you write it out, or it's capital H lowercase z if you want the short version of it. So this wave, we could say its frequency is 2 hertz. That's not very high. Sound waves, I believe people can hear in the tens of hertz. Like they could hear 100 and a little lower than that, but not much lower than that. And people can hear up to about 20,000 hertz when they're younger. When you get older, you start to lose the 20s and your limit drops to maybe 19 or 18 as your eardrums get a little bit less responsive. But sound gets up into the thousands of hertz pretty easily. If you know about a local radio station, for example, in Edmonton where I am, one of the grand old stations that's been around forever is 630 CHED. The 630 is their frequency. Their radio waves go out at 630 kilohertz, which means if you're anywhere in their broadcast range, 630,000 of their waves are going past you and through you every single second. That's the carrier wave for their station. That's an AM station. They broadcast in kilohertz. If you have a station that's something like, I don't even remember who this is. Let's say you have 98.3. FM stations broadcast in megahertz, much higher frequencies. If one of your stations is something like 98.3 or 101.3, that's the number of megahertz in their carrier wave. So that station is putting 98.3 million waves per second out in every direction, and they're going through buildings and you and everything else. And if you put out an antenna, you can pick them up, and the receiver circuit will convert that back into sound for you. So those are frequencies, always measured in hertz. And another way that you can measure this, instead of measuring how many waves you get in a single second, sometimes with slower waves we measure the other way around. We say, how long in time is each wave? For this wave here, we said this was 2 hertz, which means these 2 waves happened in a single second. Would it make sense to you that this first wave took half a second and that this next wave took another half second? We said in my simulation when I went 1/1000th that 2 waves went past this person in a single second. That means each wave took a half second to go by. That measurement is called the period. The period of something is how long does it take for it to do its entire cycle once. And so the sun's period is 24 hours. That's how long it takes for us to go from a sunrise to a sunset and back to the following morning. The period of our seasons is 365 days. That's how long it takes for us to go through spring, summer, fall, winter. And the period for this wave, it seems, is 0.5 seconds. So while frequency is in waves per second, periods are just an amount of time. It doesn't have to be seconds. It can be much longer, but for most waves it is in the seconds. So that means 0.5 seconds for a single wave. So you can measure the frequency of a wave, that's how fast waves are going past you, or the period, which is how long does it take for one wave to go past you. And that's all the terminology I wanted to show you. So if you're good with that, I'm going to clear the screen and show some basic formulae we can use to tie these numbers together. So we have lambda, which is our wavelength. We have f, which is our frequency. I should put definitions for these one last time in case you want to have it all on one page. Wavelength is distance from start of one cycle to start of the next. The frequency, oops, the frequency is waves per second. If you're just standing in one place, how many waves blow past you in a single second? The period is, if you just want one wave to go by, how long do you wait for that to happen? Big T is period. Why didn't they use P? I'm not sure. I don't remember. Right this second, I can't think of anything else that lowercase p stands for except momentum. Yeah, it's probably momentum. So they use T for time for this because capital T is the time for a single wave. And a few formulae that tie these together. One is that the frequency for a wave is 1 divided by its period, and the period for a wave is 1 divided by its frequency. So you remember from the example wave that I gave, I said that the frequency was 2 hertz. The period for it is just 1 divided by 2, and that's exactly what we found. It's 0.5 seconds. If you have something like 630 Ched, where the frequency is 630,000 hertz, the period for that station would be 1 over 630,000, which is, out comes the phone, unlock the phone, calculator app, 1 divided by 630,000. The period for that station would be 1.59 times 10 to the minus 6 seconds. So if your frequency is very high, meaning there's tons of waves going past you every second, that means the period will be very short. You're not going to wait very long for one radio wave to go through you. Just over a millionth of a second, and one wave is gone and the next wave is starting. So a high frequency like that means that instead of your wave being a big pokey thing like this, it's going to look more like, even steeper than this, but I want it to actually look like something. High frequency waves do this. They take very little time to go through a single cycle. That's a high frequency wave. This is more like a low frequency wave. Low frequency means it takes a long time for one cycle to happen. High frequency is from there to there is a cycle. It's over already. There's another one, and another one, and another one. It's knocking off cycles extremely fast. That's why you get so many in a second. So these are kind of mirror image equations, so they're relatively easy to remember, I think. Basically, 1 divided by the number you have equals the other one. You can do 1 over t to get f, you can do 1 over f to get t. So I kind of remember those as a set, which isn't too bad. And the other very important one that you'll want to know is that the velocity of a wave equals its wavelength times its frequency. So if you happen to know that water waves are going past you, you're standing here, in the ocean and waves are going past you like this. If you know that each of these waves is, say, 6 meters long, that's your wavelength, and if as you're standing there, it's a wave goes by and then another wave goes by, let's say it's one every second, so the frequency is 1 hertz. Well, if a 6-meter wave goes by and that happens once every second, it wouldn't be too surprising if the speed of those waves was 6 meters times 1 wave per second. The speed of those waves is 6 meters per second. If the waves speed up so that 2 of them are going past you every second, now you're getting 6-meter waves twice every second, and now the velocity of those waves is 12. They're going past you a lot faster, and that probably means you're getting hit a little bit harder by the water that goes by. So the velocity of any wave is its wavelength multiplied by its frequency. Definitely worth knowing. And last one, which won't surprise you, it's just a little tweak. We saw up here, frequency is 1 over period. So if you take V equals lambda f, I'm going to erase the f, and in its place I'm going to put 1 over t, and lo and behold, we'll have another formula. Clean that up a little bit, and you get the velocity of a wave is its wavelength divided by its period. That kind of makes sense because wavelengths are measured in meters and periods are measured in seconds, so if you divide those, you would get something in meters per second, which is exactly what a velocity should be, shouldn't it? So, honestly, I've never bonded with this formula. I don't exactly have it memorized. I have to derive it anytime. I'm more used to working with this formula, and then if I need the frequency, I know I can calculate it by doing this side thing. So V equals lambda f is the one I carry around in my head. If you want to memorize both of these, terrific. I believe this is the one that's on your formula sheet. And actually, one second. Yeah, our formula sheet gives you this. They write f lambda, which is of course the same thing, and they give you t equals 1 over f. So these two are what's on Norquest's sheet. So no need to memorize either of these, of course. This is, just remember that you can swap these two variables, and I think most people retain that without too much trouble. And it's up to you if you want to memorize this one. I can report that never really having memorized this one, I did fine. Just make sure you know the lambda f version, and you can adapt your work to that. So that's like lesson 1 about waves, some measurements we can take with them, and some numbers that you can be given about waves. Hope that's helpful, and if there's anything else that you wish we had mentioned about waves, let us know, and we'll build some more of these.